All right, we left off talking about the markings on bones and what these, I'm just giving examples here, but also telling you reasons why we might have these. So here's our four groups. I add on here depressions, right? So we've gone through articulations where they meet, projections where we're going to have attachments to bones, and holes that allow blood vessels and nerves basically to pass through oftentimes, as well as like your auditory canal for sound, right? Depressions are there to accommodate soft tissue. So you see an awful lot of depressions in the skull, especially the cranium, and depressions in the coxa, the hip bones, to accommodate your organs and the scapula and places like that. All right, so I mentioned this already in a on the previous video, but let's look formally at this idea of the characters and where we find them in regards to changing bone, because bone is, again, a very, very dynamic tissue. So here you see these osteocytes, and those are really evident on the models and on the slides. That's what you saw when you looked at, bone tissue for the first practical. And then we have, and we say these are the maintainers of this matrix, right? The osteoblasts, well, blasts are builders, right? So they made the matrix. Osteogenic cells are basically undetermined cells. I mean, that will become some sort of bone cell, but could become the other types, right? So this is we call this a precursor cell, kind of the parent cell that helps you. But stem cells undetermined, so osteogenic, generating, bone generating. And then the osteoclast, which is a unique looking cell that helps to reabsorb bone. And you'll notice how they kind of place these on the cartoon to show you that you build this bone from the outside, and then you reabsorb it here from the inside, basically. So you're always building out, but also taking from the inside, and that helps to maintain this ratio of compact osseous bone to marrow, and again, make sure that bone is functional and doesn't get too heavy. I say here that cell activity is balanced. Production and destruction of bone is there to suit your needs. So your biggest need is going to be for blood calcium levels, and in that case, these guys will become very active, and we'll see how that happens in this chapter. So matrix, again, like this is a connective tissue, so the matrix is made by the cells, and the blasts are the ones that do this, right? The cells, the osteogenic ones, divide and produce the different cells from the osteogenic cells in the deep periosteum and the marrow. We were looking previously at the endosteum on a previous slide, but they are also found just beneath the periosteum, so on the very inside and outside, right? Osteoblasts don't divide on their own and are found in the periosteum and some in the endosteum. Osteocytes are found pretty much in these areas in between. So all this compact bone, because it's a maintainer, would be osteocytes. They generally are found in a space, an anatomical space we call the lacunae. The chondrocytes or cartilage cells have this as well, and they connect to each other through these little tiny canals, therefore called canaliculi, and look like these little fractures almost on the bone, giving that really unique shape. All right. From monocytes and macrophages, so these guys are not actually produced by the osteogenic cells. The osteoclasts come from, these are blood cells, right? So monocyte is the blood cell. It converts to a macrophage when it leaves the blood, and bone, of course, will be outside of the blood. But they will be then, due to gene expression, change or develop into osteoclasts, and we'd find these on the bone surface, right? And they would be kind of reabsorbing that bone and then depositing calcium into the blood. So why do we have this compact and spongy? And again, this should look very familiar to you. It's just an image of some compact bone. So compact and spongy, to have some differences. And the reason I knew that right away is because this feature is unique to compact bone. It's the central canal. In the central canal is basically artery, vein, arteriovenule, lymph, and nerves. All right, and so this space here allows, the a lot of vasculature and fluids to be transmitted and sensation to occur in bone. So the central canal is a defining point that the osteocytes get organized around. And so you get these, right, concentric circles radiating out from the central canal. And of course, the osteocytes depend on nourishment from that central canal, so you can't grow too far away from that because this, again, bone is pretty dynamic. All right, so this just shows you, again, here's our periosteum and the blood being delivered in and then moving underneath this, right, within this connective tissue here, and then branching and being delivered. So these are perforating canals, or sometimes called Volkmann's canals, and they then branch again to produce central, right, the central canals, and perforate again central canals. Okay, so compact bone is going to have a whole lot of this. All right, now compact bone is there to basically resist compression, right? This is the support, it's the columns. So each of these, right, we call the whole thing an osteon. So each of these, and an osteon is a unit of the bone. And that osteon is really running the whole length. So these are like multiple mini columns and just packed with this. So an amazing amount of support and protection by this basic design. All right. Again, osteons are the units. They have lamellae. That's the name for these layers. They have a central canal where you see the blood vessels able to move through the bone, right? And perforating canals so blood vessels can move between the osteons. Okay, so compact bone is on the outside of every single bone, but on flat bones, irregular bones, things like that, it's very, very thin. In the epiphyses of long bones, it's very thin, but in the diaphyses, right, the support column, there's a lot of compact bone. All right, spongy bone is a different design. They do not have a central canal, so here's our, osteon for all intents and purposes. All right. And this is very active. You see these osteoclasts, and like we looked at in a previous slide, so we see a lot of osteoclasts here and osteoblasts, and they do remain very closely associated with each other. And whereas this one would build and this one would reabsorb, and they need to balance their activity. And then, of course, lots and lots of osteocytes in their spaces, right? So osteocytes in the spaces. But no central canal. No central canal is needed because these osteocytes are never very far from a blood supply. All right. So because of this branching and not a compact, right, just a tightly packed bunch of osteons, but just osteons in forming these network, we don't have to bother with the organizing central canal in spongy bone. Spongy bone is a shock absorber, and it helps to redistribute the weight of the bone. Like I said, we really don't want solid bones. Movement would be very difficult in this circumstance. We also call spongy bone cancellous or trabecular, and we find these in the epiphyses. We find these in flat bones, in irregular bones, right, sesamoid bones, right. So they make up the majority of those bones. But in long bones, we tend to see the spongy bone at the epiphyses, where we're articulating or meeting another bone. So these are able to take and withstand a lot of shock, whereas compact bone would transmit the shock. These guys would absorb it. So this is a very important physical state of bone. All right, and again, not concentric lamellae. They kind of show that, but they're not organized around that central canal. All right, how does bone develop and form? So, you've come a long way in many ways when you look at yourself in the mirror and you think about what you are. Remembering again, you started from one cell, right? That zygote from mom and dad. So the process of producing bony tissue or osseous tissue is called ossification. Okay. Well, now it turns out if I had an image of a embryo, right? Because embryo is basically from about conception to 8 weeks. And then 8 weeks to 38 weeks is your fetus, or the end of 8 weeks to 38 weeks is a fetal stage, okay? And so during the embryonic stage, you remain very, very small, but you are building all the components of what's going to be important. We're trying to get everybody in a place in the body organized. And so if you look at an image of an embryo nearing the fetal stage, you see a little human, right? You see fingers and toes and arms and legs and a skull and everything. Well, it turns out that's all cartilage, right? And in fact, some of it will remain cartilage for a very long time. And there's a reason for this as well, right? But so the cartilage provides the shape. That's why you look human. I said bone is ultimately now is your shape. The cartilage is going to allow you to continue to grow, right? The bone, right? Once the cartilage is used up in bone, bone doesn't tend to grow much. All right, it remodels, but it doesn't grow much. And this is especially true in our long bones, right? Where that's where our height, what we judge our growth by. All right, so stuff to think about. So somewhere in the fetal stage, we said that's week 9 to week 38, you must begin the task of converting some of this cartilage to rock. Because when you're born, you're going to need to have better support than cartilage would give you, right? And you're going to continue to do these conversions throughout your life. In fact, if you had it all converted by birth, you wouldn't get any taller. So the ossification process is a long, drawn-out process, taking you into the second or third decade of your life. All right, and you definitely want to begin ossifying the things that you're going to need for support. So again, ossification is the process of converting, cartilage basically to bone. And so osteoblasts are driving this process, but they are going to need assistance from osteoclasts and a few other cells. So, all right, it begins again about the fetal stage. It ends, in the third decade or so of life. And the long time really reflects this ability to, the trade-off of having the flexibility of cartilage and ability to get taller and not need as much support to eventually needing that support. Okay, so the overview is that you have two basic processes. You have a process called intramembranous and a process called endochondral. And so the majority of the skeleton forms by the endochondral. So cartilage is, again, your entire template right now is an embryo becoming a fetus. And so in the intramembranous, it's not cartilage that actually gets converted, but some dense regular connective tissue. So this is what forms basically in the skull your collarbones and your sternum. So not many of your bones, but they would be a different starting material. They basically form very similarly, though, despite this difference that we talk about here. So these other connective tissues, right? This of course being a connective tissue proper, this being cartilage is a supportive connective tissue, but not that strong, right? Cartilage, both of these would be converted, and cartilage and dense connective tissue is used as a framework, all right? So they've established a template or the basic shape, all right? But you're not going to get the support you need with cartilage. So these chondrocytes, especially in the endochondral, need to be replaced with osteocytes. So I ask students to know the roles for osteoblasts, osteoclasts, and chondrocytes, as well as the osteocytes, which we've kind of gone over some of these already. So we're just reinforcing this in this part. All right, so in intramembranous ossification, here's the situation, all right? And again, you'll notice that I said this is really bones of the skull, clavicle, and sternum. And so we're going to end here with this, lots of spongy bone surrounded by some compact bone eventually. So we begin here with all these pretty undetermined cells called mesenchymal cells and a lot of collagen. Collagen gives us flexibility. And somewhere, again, in the fetal stage, you would start with a few cells being converted because gene expression changes, and osteoblasts being formed from osteogenic cells, all right? And this, again, I'm not going to ask you to know all these details, but eventually the osteoblasts would begin producing bone, right, or osseous tissue, and they'd be converted, some of them would be converted to osteocytes, the maintainers, and we'd perpetuate this kind of basic ring, and we would radiate out, converting this generic mesenchymal tissue, again, which is like a dense regular with lots of collagen, to bone. All right? So the mesenchyme will form the periosteum. You still have these, right, osteoblasts. that are lining up on the outer part, and they're just converting, right, the basic generic connective tissue to bone, right? So it doesn't involve chondrocytes or osteoclasts, but there's a conversion of mesenchymal cells to osteogenic, sorry, misspelling, to osteoblasts, which secrete osteoid, this, again, osseous, and trap them, converting them to osteocytes.